Hello everybody, we meet again today for next topic on current. Today we will look at what is current and the relationship of current between electrical charge and time. Then, we will discuss on scientific notation. I will also explain few examples throughout these two topics. Current. The atom has been defined as the smallest particle of an element. It is composed of electrons, protons, and neutrons. Electrons breaking away from atoms and flowing through a conductor produce an electric current. This chapter examines how electrons break free from atoms to produce a current flow and how to use scientific notation. Scientific notation expresses very large and small numbers in a form of mathematical shorthand. Electrical charge. Two electrons together or two protons together represent like charges. Like charges resist being brought together and instead move away from each other. This movement is called repelling. This is the first law of electrostatic charges. Like charges repel each other as in figure. According to the second law of electrostatic charges, unlike charges attract each other. The negative electrons are drawn toward the positive protons in the nucleus of an atom. This attractive force is balanced by the centrifugal force caused by the electron's rotation about the nucleus. As a result, the electrons remain in orbit and are not drawn into the nucleus. The amount of attracting or repelling force that acts between two electrically charged bodies depend on two factors, their charge, and the distance between them. Single electrons have a charge too small for practical use. The unit adopted for measuring charges is the coulomb, c. named for Charles Coulomb. The electrical charge, Q, carried by 6 quadrillion electrons, or 6.24 times 10 to the power of 18 electrons represents 1 coulomb. Electrical charges are created by the displacement of electrons. When there is an excess of electrons at one point and a deficiency of electrons at another point, a difference of potential exists between the 2 points. When a difference of potential exists between two charged bodies connected by a conductor, electrons will flow along the conductor. This flow of electrons is called current. Current flow, an electric current, I, consists of the drift of electrons from an area of negative charge to an area of positive charge. The unit of measurement for current flow is the ampere. An ampere represents the amount of current in a conductor when 1 coulomb of charge moves past a point in 1 second. The relationship between amperes and coulombs per second can be expressed as follows. Current measure in ampere. I is equal to quantity of electrical charge in coulombs, Q, divided by time in seconds, T. Example, what is the current in amperes? If 9 coulombs of charge flow past a point in an electric circuit in 3 seconds. Given in the question are, electrical charges, Q equals 9 coulombs, and time, T equals 3 seconds. And we need to find electric current, I. Using the equation given in previous slide, we need to divide Q by T. In this case we divide 9 coulombs by 3 seconds. By doing this we will get I equals 3 amperes. Example, a circuit has a current of 5 amperes. How long does it take for 1 coulomb to pass a given point in the circuit? Given in the example are electric current, I equals amperes, and electrical charge, Q equals 1 coulomb. And we need to find time, T. Using the same equation, I equals Q divided by T, we substitute all the given values. By using cross multiply, we get 1 equals 5T. By bringing 5 to the left-hand side of the equation, we will get 1 over 5 is equal to T. This is mean that time, T is equal to 1 over 5 second or 0.2 second. Electrons, with their negative charge, represent the charge carrier in an electric circuit. Therefore, electric current is the flow of negative charges. Scientists and engineers once thought that current flowed in a direction opposite to electron flow. Later work revealed that the movement of an electron from one atom to the next created the appearance of a positive charge, called a hole, moving in the opposite direction as is in figures. Electron movement and current were found to be the same. If electrons are added to one end of a conductor and provision is made to take electrons from the other end, an electric current flows through the conductor. As free electrons move slowly through the conductor, they collide with atoms, knocking other electrons free. These new free electrons travel toward the positive end of the conductor and collide with other atoms. The electrons drift from the negative to the positive end of the conductor because like charges repel. In addition, the positive end of the conductor, which represents a deficiency in electrons, attracts the free electrons because unlike charges attract, the drift of electrons is slow, approximately an eighth of an inch per second, but individual electrons ricochet off atoms, knocking other electrons loose, at the speed of light, 186,000 miles per second. For example, visualize a long, hollow tube filled with ping-pong balls as in figure. As a ball is added to one end of the tube, a ball is forced out the other end of the tube. Although an individual ball takes time to travel down the tube, the speed of its impact can be far greater. The device that supplies electrons from one end of a conductor, the negative terminal, and removes them from the other end of the conductor, the positive terminal, is called the voltage source. It can be thought of as a kind of pump as in figure. In electronics, it is common to encounter very small and very large numbers. Scientific notation is a means of using single-digit numbers plus powers of 10 to express large and small numbers. For example, 300 in scientific notation is 3 times 10 to the power of 2. The exponent indicates the number of decimal places to the right or left of the decimal point in the number. If the power is positive, the decimal point is moved to the right. For example, 3.0 times 10 to the power of 3. Because of power is by positive number of 3, then the decimal point will be moving 3 times to the right, which is equal to 3000. If the power is negative, the decimal point is moved to the left. For example, 3.0 times 10 to the power of negative 6. Because of power is by negative number of 6, then the decimal point will be moving 6 times to the left, which is equal to 0.000003. Figure lists some commonly used powers of 10, both positive and negative, and the prefixes and symbols associated with them. For example, an ampere is a large unit of current that is not often found in low-power electronic circuits. More frequently used units are the milliampere and the microampere. A milliampere is equal to 1,000th, 1 over 1,000, of an ampere, or 0.001 A. In other words, it takes 1,000 milliamperes to equal 1 ampere. A microampere is equal to 1 millionth, 1 over 1 million, of an ampere, or 0.000001 A. It takes 1 million microamperes to equal 1 ampere. Example: how many milliamperes are there in 2 amperes? For this example, we know that 1 ampere is equal to 1000 milliamperes. So, we can write as in the left-hand side of the equation, which is 1000 milliamperes over 1 ampere. This is equal to the right-hand side of the equation, which is x milliamperes over 2 amperes. Here, we need to find the value of x. By using cross multiply, we 1 multiply by x on the left-hand side of the equation, and 1000 multiply by 2 on the right-hand side of the equation. Then, by solving this multiplication, we will get x is equal to 2000 milliamperes. In this next example, how many amperes are there in 50 microamperes? To solve this question, we need to know how many microamperes are equal to 1 amperes. Based on previous explanation, we know that 1 ampere is equal to 1 million microamperes. Therefore, on the left-hand side of the equation we write 1 million microamperes over 1 ampere. This is equal to the right-hand side, which is 50 microamperes over x ampere. By using the same approach as previous example, we cross-multiply both sides to get 1 times 50 equal to 1 million times x. Solving this equation will have x equal to 0.00005 amperes. We will stop our class today at this topic. Please check the note that I have attached on online learning for more exercises on this topic. If you have any problem regarding to the topic or exercises, please feel free to ask on the WhatsApp group. Hopefully, any other students will be able to solve the problem. If no, I will try to solve the problem. Thank you, and we will meet again on Wednesday.